Welcome to Maths with EJD. In this video, we're talking about Laplace transform for stability analysis. Now, we've done a lot of work on stability in the past using ideas like eigenvalues and eigenvectors and all that. So it's interesting to know that we can actually use Laplace transform for stability also. So let's see how this comes. So as an overview, so the Laplace transform is a critical tool for analyzing dynamical systems, particularly in control theory and engineering. It transforms time domain, differential equations, time domain differential equations into algebraic equations. I mean, we've done this a couple of times, but I mean, this video may be the only one some people will ever see. So into algebraic equations in the complex frequency domain. In the complex frequency domain, simplifying the analysis and solution of these systems. Solution of these systems. Okay. Additionally, it is used to assess system stability by examining the location of the poles, which of course we also know poles as points of singularities or points of discontinuities, examining the location of the poles of the system's transfer function in the complex plane. So as we know already, right? Uh, definition of the Laplace transform, it's well known. We've done that quite a lot, but let's just repeat for emphasis. Definition of Laplace transform. So the Laplace transform of a function f of t denoted by L of f of t equals fs. F of s is defined as the Laplace of f of t, which is f of s, is the same thing as integral from 0 to infinity of e raised by minus st f of t dt. So this is standard and we've used it a lot. So where t is the time variable, then s, which is sigma plus j omega, is the complex frequency variable. complex frequency. This is the first time I'm really explicit about this. Is a complex frequency variable with real parts sigma and imaginary parts j omega. Then we have f of s. F of s is the Laplace transform of f of t. Okay, so let's switch things up a bit now. Um, let me bring this. Okay, so stability analysis using Laplace transform. So that's the key of what we're doing here, using Laplace transform. Okay, so the stability of a system can be determined by analyzing the poles of its transfer function. Okay, these poles are the values, they are the values of S where the denominator of the transfer function becomes 0. Okay, the location of these poles, the location of these poles in the complex plane determines the system's stability. First of all, we have a stable system. So for a stable system, all poles have negative real parts. All poles have negative real parts. That means they are located in the left half of the complex plane. Okay, so in that case, we have a stable system, and we have what can be an unstable system. Unstable system. So for an unstable system, any pole has a positive real part. So once one pole has a positive real part located, that is located in the right half, in the of right half of the complex plane. Once there's a pole like that, then we have an unstable system. And we also have what we can call a marginally stable system. Marginally stable system. So for a marginally stable system, here poles lie on the imaginary axis. Poles lie on the imaginary axis, but are not at the origin. Or they are not at the origin. So in that case, we say such a system is marginally stable. So we switch over now, and I go for Let me go for this after a long time. Okay, so let's take an example. Let's take example one. I think we're going to take a couple of examples here for the first one is a first order system. First order system. Okay, so consider a first order linear system described by the differential equation how dy of t dt plus y of t equals u of t. Okay, u of t is the output and y is the input, right? So, and tau, where tau is the time constant, the time constant, the time constant, and u of t is the input. U of t is the input, of course, and y of t would be the output. So here now, taking the Laplace transform, taking the taking the Laplace transform of both sides. So, I mean, we are used to this already. So if we take the Laplace transform of this expression, that will simply be tau, because Laplace transform of y, dy dt would just be sys, that would be sys minus y naught. So we just have tau multiplying all those out. Okay. Okay, let me not rush. Let me not rush. Since this may be the only video somebody may see about this. So let me just take my time. So taking the Laplace of both sides now. So we are simply going to have the Laplace of tau dy of t dt plus y of t. And that is the Laplace of u of t, basically. So that means that we have yeah, so we have that. So it means we have tau Laplace of dy of t dt and plus the Laplace of y of t. Okay. And that is equal to the Laplace of u of t. And if we deal with that, we have tau out here into the Laplace of dy of t dt is simply s y of s minus y of 0, like the initial condition, plus the Laplace. So Laplace of y of t is simply another y of s. The Laplace of u of t is u of s. Okay, now in the complex frequency domain. So in this case, we can open this up. So tau multiplies all this. So we have tau s y s, y of s minus tau y naught plus y of s equals u of s. So we can keep the taus together and transfer, I mean, we can keep the y of s's together, right? And we can transfer this one because that's no y of s. So we have tau s y of s plus y of s equals the u of s on that side plus tau y of 0. So y of s is common, so we have y of s into tau s plus 1. All right, and that is equal to u of s plus tau y of 0. So if we make y of s the subject, so that will be y of s equals u of s plus tau y of 0 all over tau s plus 1. So this is our y of s now. Okay. So from here, the pole of the system, the pole of the system is found by setting. So in this case, now what we are simply saying is that this now, okay, yeah, let's just go. The pole of the system is found by setting the denominator, the denominator equal to 0. So what that simply means is that we have tau s, we have tau s plus 1 equals 0. And that simply means that that means we have tau s equals minus 1. That means that s alone is minus 1 over tau. So this is the pole in this case. So it's negative. So we can say that since the pole since the pole has a negative real part, since the pole has a negative, so this is minus 1 over 2, which is real, not complex. Even if it is complex, this is the real part, it's still good. So since the pole has a negative real part, that is that's when we assume that tau is greater than 0, that tau is positive, so that'll be a negative real part. Okay, since the pole has a negative real part for tau greater than 0, the system is stable. Okay, so we have a stable system for that negative value. So let's take another example. So let's switch over to this now, and then maybe have this. Okay, does that make sense? It's been a long time, let me do blue. Okay, so another example, example 2, where we take a second order system. So for a second order system now, okay, um, consider a second, order system described by y prime prime of t plus 2 eta wn y naught y dot t plus wn squared y of t equals u of t. So if you consider that, where omega sub n or w sub n is the natural frequency, and eta is the damping ratio. Okay, so if we have that now, taking the Laplace transform of both sides, okay, what do we have? Okay, I think okay, well, let me go gently. Okay, so we have, but I'll just be as fast as possible. So we have the Laplace of y dot dot of t, okay, then plus 2 eta wn Laplace of y dot t as first derivative, then plus wn squared, the Laplace of y of t, and finally the Laplace of u of t on the right hand side, u of t. Okay, so if we open that up now, so here y dot dot of t, the Laplace, that would just simply be s squared y of s minus s y of 0. Okay, then plus minus sy of 0, right? And then we have minus y dot of 0. Okay, so that's for this first one now. For the second one, we have 2 eta omega n. So, and that will be sys minus y of 0. Okay, that is for this now. Okay, that is for this. Then the next one now, we have, okay, still on this. So we have plus wn squared. The Laplace of y of t is simply y of s, and this is equal to u of s on the right-hand side. So if we take it that if we take it that all the initial conditions are zero, okay? So we say for we take y of 0 equals 0, and we also take y dot of 0 equals 0. Okay, if that is the case, now it means this will go, and this will also go. So we can then have s squared y of s squared y of s. Okay, then the next thing 2 eta, so plus 2 eta wn y of s. Then the last one, we have this now, wn squared y of s plus wn squared y of s, like that. And that will be equal to u of s on the right-hand side. When we take the Laplace, yeah, we already think that that's u of s. So if you take all of those things to be 0, so in this case now, we can take out y of s. So y of s, we have y of s into s squared plus 2 eta wn. Okay, 2 eta wn. I think I've skipped a particular s here. wn, wns, yes. wns, okay. So that s comes in here, then plus wn squared, and that is equal to u of s. Okay, so it means that y of s now is equal to y of s is equal to u of s all over s squared plus 2 eta wns plus wn squared. Okay, so we have that. So this is the expression for y of s. But then we have the we're talking about transfer function the other time. So the transfer function is g of s, and that g of s is simply 1 over s squared plus 2 eta omega ns plus omega n squared, or wn squared, whatever you want to call that. So this is the transfer function now. So here we now have to bother about the poles of this. So the poles are determined. The poles are determined by solving the characteristic equation. The characteristic equation, this expression down there. So that will be s squared plus 2 eta omega ns plus omega n squared equals 0. So we are solving for s now. So we get the poles by solving this. So the roots are, of course, we know that should be s equals minus b. So minus b now will be the coefficient of s, right? That's 2 eta omega n, okay? 2 eta omega n, then plus or minus square root of the same b now. That's 2 eta omega n all squared minus 4. A is 1. That's the coefficient of s squared. C is omega n squared all over 2 times 1. Okay. So in this case now we have s equals minus 2 eta omega n plus or minus square root of 4 eta 4 eta squared omega n squared, then minus 4 eta 4 omega n squared also, like that, all over 2. So s now is minus 2 eta omega n plus or minus. So here square root of, if you factorize this, we have 4 omega n squared, right, into eta squared minus 1, like that, all over 2. So from this, we can have that we have s S is equal to minus 2 eta omega n plus or minus. So we can take the square root of this out. So we have 2 omega n into eta squared minus 1 all over 2. So if we divide through by 2, we simply have S to be minus eta omega n plus or minus omega n square root of eta squared minus 1. So these are the poles here, are the poles right here. So for this now, we can have the following conditions. Okay. So it can be undamped. It can be this is undamped system. So we can say the system can be undamped. Oh, the system can be first of all undamped. So if it is undamped, it means that 0 is less than eta is less than 1. That means if eta lies between 0 and 1, so the system will be undamped because the poles are complex. It can be undamped if the poles are complex with negative real parts, and the system is stable but oscillatory because of the complex nature. That's one. Then the system can be critically damped. It can be critically damped. It can be critically damped if eta is equal to 1. So if eta is equal to 1, so what is going to happen here? So that'll be 1 squared minus 1. 1 squared is 1 minus 1. So this, all the negative parts, all the other parts will go for sure, and we just have only this expression left. So in that case, we just have a negative value there, meaning all the way it is kind of stable. So the system is stable. The system is stable with no oscillations, and the fastest settling time, because it's not oscillating, and the fastest settling time. Now we can also have overdamped. It can be overdamped. The system can be overdamped. In that case, eta is greater than 1. So, all right. So in that case, we have that the system is stable, right? But slower to reach steady state, or slower to reach steady state. Okay. All right, let's switch over to this now. Let me go back to the bright colors. So let's take example 3. Example 3. I want to cover all the possibilities so it can be comprehensive enough. So what if we have an unstable system altogether? Have an unstable system. How does this go? So consider that after you've done everything, consider a system, after you've done the transformation, consider a system with the transfer function. So we go straight to the transfer function now. With the transfer function, g of s, which is equal to 1 over s squared minus 2s plus 1. So consider a system with this kind of thing. So you see that the characteristic equation, the characteristic equation is s squared minus 2s plus 1 equals 0. Okay. So solving for s now. Solving solving for s, we have that s is equal to b, in this case is -2. So we have -2 plus or minus square root of -2 squared minus 4 into a. A is 1 because coefficient of s squared is 1, and c is also 1, all over 2 times 1. So we have s to be 2 plus or minus square root of 4 minus 4. Okay, square root of 4 minus 4 all over 2. So that's s equals 2 plus or minus square root of 4 minus 4 is simply 0 all over 2. So it means that s is simply 2 over 2, and then s is 1. S is 1. That is real and it's positive. Okay, so we can just say since since the pole is at s equals 1, which is in the which is simply positive, which is in the right, it's in the right half of the complex plane of the complex plane. Okay, the system is simply unstable. The system is unstable. Okay, the system is unstable. So that that's how far that goes. Okay, so can we also should I make this into a third order video? Oh, okay, let me just deal with this and let it. I'm really thinking. Okay, yeah, let's stop here. I'll continue stability for third order systems, right? So I can emphasize on the idea of the Routh-Hurwitz criterion for third order systems, you know, using Laplace transform. Okay, so I'll push that to the next video. So let's take some practice questions, if we may. Um, okay. Mm, yeah, I think I'll just pass in this case. Mm, okay, I mean, let me do one and just one or two at least. Practice, practice. Um, given the given the second order, given the second order characteristic equation, s squared plus 6s plus 9 equals 0. Okay, this is 1 now. Okay, given that A, find the poles of the system and the poles of the system. Yeah, it looks basically like the idea of eigenvalues too. Is the system stable? Is the system stable? Then justify your answer by analyzing the real parts. Justify your answer by analyzing the real parts of the poles. Okay, so that is what we have for now. Okay, let me take a second one. The questions are looking attractive to me actually. So this is one now. Let's do the second one. Two. Given the characteristic equation, from the characteristic, that's after doing all the Laplace transform, everything, you end up getting this. Given the characteristic equation, s squared plus 2s plus 2 equals 0. So A, A, find the poles of the system. Find the poles of the system. B, determine the damping ratio. Determine the damping ratio, eta, and the natural frequency. So you have to compare it with where we're coming from. And the natural frequency, omega n, for the system. So you have to compare with that second order system we did. All right, so let me see your answers in the comment section on Facebook or on YouTube. And of course, let me also know how helpful these videos are for you. And if there's a topic you'd like me to teach or a problem you'd like me to solve, feel free to let me know also. If you have subscribed to this channel, thank you. If you have not, please go ahead and do that right away because you have a lot coming and there's a lot there already for you to learn. You also want to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to hit to comment, like, and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.